All right. So today I want to go over structures, typedefs, a few things C-like that will help you with both the ODP and with your programming assignments. So I want to do a bit of a refresher on some of these things in C. And then I want to talk about ODP 202, which posted this morning and is due tomorrow morning at 8. And then I want to go ahead and look at the details of programming assignment 1, which has been on Canvas for a few days. So we'll start digging into the details of that. Before we get going on that, any questions? Does everybody here have access to the Linux server now? Okay, if you don't, definitely come and talk to me like as soon as possible, because we got stuff going on there now. All right, so let's talk about structures. So a common thing to do in programming is to use something that we call parallel arrays. And the idea is, for example, suppose you're processing student information, and you have student names and student IDs and grade for the student, a GPA, right? So you have 3 pieces of information per student. And one way to manage this in something like C is to make 3 arrays. You can have an array called names, an array called GPAs, and an array called student ID. And element 0 has a name, and that person's student ID is in element 0 of the student ID array, and their GPA is element 0 of the GPA array, right? And we could make these arrays 1,000 elements long, and now we can store information about 1,000 students in these 3 arrays. The downside to using parallel arrays is, one, you've got to move around multiple pieces of information. If I want to call my print routine, I've got to pass the name array, the student ID array, and the GPA array. If you manipulate this information, if you're sorting, for example, you have to keep these things in sync. So if I swap 2 elements in names, I have to swap the same 2 elements in all my other arrays. And it's just kind of cumbersome. So most languages, including C, give us a way to take multiple pieces of data and gather them together. And the way to do this in C is to use what's called a structure. And the syntax is the keyword struct, followed by what you want to call the structure. So let me just call the structure student. And then you have curly brackets and a semicolon. And in between the curly brackets, you list all the different fields that make up this structure. So for example, I might have a name, which is 32 characters. I might have a student ID, which is an integer, and I might have a GPA, which is a double. And these are just regular variable declarations, but we're not actually making a variable called name, SID, GPA. We're defining fields within this composite data type called a struct student. So now I can say I want a variable that represents a student. I could say struct student S1. So S1 is a struct student, which means S1 contains a name, a student ID, and a GPA. And if I want to initialize the student ID of this student S1, I do the following: S1 dot SID, and then whatever you want to do with it. So S1 is the name of the variable, the name of the structure. SID is what we call a field. Okay, there's 3 fields inside the structure: name, SID, and GPA. So I'm setting the SID field equal to this number. And if I want to increment their GPA, right, I could do S1.GPA equals S1.GPA plus 1. Can't think of a reason why you would ever do that. All right, so you know the basic idea, right? And you've done this in 121, or at least talked about it, right? Okay. So let's write some code. Okay, so this is a structure that can hold information about one student, a name, a student ID, and a GPA. Doesn't matter how long I make it, I'll just make it 32. All right, so let's make a main program. So I'm declaring a student named S1, and I'm setting values into two fields. What?
You don't need to include standard library?
So far, I don't even need to include standard I/O because I'm not doing any I/O. So standard library, standard I/O, you include these things if you're using certain functions. Standard library, generally we include if we're going to use malloc. Standard I/O, we usually just include out of habit, but if we're doing printf, fget, scanf, things like that, we want standard I/O. So I'll want it eventually, but I don't think we're going to need standard lib or C type. Right, so I can compile that up, but it's not going to do anything because all I'm doing is setting some values to some fields. Okay, I want to give a value to the name field of this student. Well, s1.name is a character name, bracket 32. It's a C string, which means I can use it as an argument in something like string copy, and I can say string copy Nick into that character array.
Does string copy exist in standard I/O?
Yes.
Okay.
No. It might be in strings. Let's find out. Yep, it's in string. All right. Thank you. Well, the reason we're doing this in part is because now if I want to do something like print out the information about the student, I don't have to pass all these different pieces of information. I can just pass the name of the student, in this case S1. So let's say call myPrint S1. And I'm going to write a function called myPrint that takes this struct student and prints out their name and student ID and GPA. So I'll prototype the myPrint function. It's not going to return anything, so the return type is void, and it takes a single argument, which is a struct student. So let's print out student info. So I'm just going to call my argument A to be deliberately vague. And to get to the name, I just say a.name. And a.name will be a character array. And a character array is exactly what I want to pass to printf if I'm saying %s. And we'll print out the student ID. I can never remember how to print doubles.
I think it's LF.
I was going to do G, but we'll try that. So let's print out the GPA, and then let's just return. We may get something weird on the GPA. That's pilot error. Hey, thank you. All right, so student name, student ID, student GPA. And the whole point of this is to do this print, all we had to do was say my print, and we just passed the name of this variable that had all this information in it, right? And then my print takes it apart by accessing these different fields. So that's the whole essence of a structure. Now, any time that we want to use a struct student, we have to say struct student. And that's a little cumbersome. It's not terrible. But we can make this a little cleaner by using a typedef. So typedef is a statement in C. We use the keyword typedef, space, and then we list. Typedef is a way to make a pseudonym for some other type. Okay, so we list the type that we want a pseudonym for. So I want a pseudonym for struct student. And then we list what we would like to use instead of having to say struct student. And I'm just going to call this a student with an uppercase S. So after this typedef statement, anytime I say student with an uppercase S, it means struct student. So it's an abbreviation, basically. I don't know if I need a semicolon or not. I do. So now, instead of saying struct student, down here, I can just say I'm taking one argument of type student. And down here, instead of saying struct student S1, I can say uppercase student S1. And down here, instead of struct student A, I can just say student A. It doesn't buy you any special functionality. You can't get away with just saying struct student. But we're used to saying integer A, character C, double X, right? And this lets us sort of continue that sort of simpler notion of saying, okay, student A. And A is a student. So this does exactly the same thing, but it's a little cleaner to read. Okay, and the last thing I want to embellish on here is if we have an array of structures, which is perfectly valid. So S1, let's make an array of 100 students, and we'll call the array S. And so S bracket 0, let's set element 0. So now element 0 of our student array is Nick with a student ID and a GPA. And we have another student named Nick 2. And we're going to store them in index 1 of our student array. And they've got a lower GPA and a strange student ID. And I'm going to pass this entire array of student information to the myPrint function by just passing the name of the array, S. well, let's do it like this. I'll change my print, so I take the array and I also take an index. So my print will take an integer. So I'll pass the array plus an index location to the myPrint routine, and I'll just print out the fields from that corresponding element. Right, so if I call myPrint S1, it should print the information in Nick 2. And up here, I have to say student star A because A is an array. I could also say student A bracket 100 if I knew it was 100 elements, but it's safer to just say star asterisk A, and then whatever size array it is, doesn't matter. I knew that was too easy. So the first argument is a pointer to a student, the second argument is an integer. And I forgot a semicolon. Alright, so we run it and there's the information on student 2. And if I called myPrint with an index of 0, I'd see the information on the first student. And what if I call it with an index other than 0 or 1? What if I try to print student 5? What's it going to do?
Would likely seg fault because, or print random information because there's nothing.
Those are your two options. It's probably not going to seg fault because the array actually does have an element 5. But if I go into and I try to print the name, it's possible that the name would seg fault, but I don't think it will. But we'll see. Pretty boring. So things were mostly initialized to 0. That may or may not happen, and it may change from day to day and from machine to machine. But if I use a crazy index, of course, I'm more likely to get a seg fault. Right, because now I'm just going outside the bounds of the array, significantly outside. All right, makes sense? So let's look at the ODP. So ODP 202, arrays of structures. Look at that. So you're going to define a structure. You need to call your structure node, and it needs to contain 3 fields. They're all integers. The first field is called data, and then next, and then valid. And you've got to define them in that order. Okay, this is important. It makes a difference to the compiler. So you define a structure named node, and then I want you to make a function named init. And init takes an array of these struct nodes. You can use a typedef if you want, so you don't keep saying struct node, or you can just say struct node. So init takes a pointer to a struct node, right? That's an array. And your function should assume this is an array of 100 nodes. And it should do the following. Element 0, it should set the valid flag to 1, the data flag to 42, and the next field to -1. And all the other 99 elements, it should set valid to 0, data to 999, and next to -99999. So it's an initialization function. And it gives initial values to every field of every element of that array that you pass to it. Okay, so do that and test it yourself. Write a main program. Make yourself an array of 100 of these struct nodes. Call your init function, right, passing the array to it, and then try to print out some of these fields. Print out those 3 fields from element 0, print out those 3 fields from maybe element 1 and element 99. Right? And if you've got those fields correct, probably all the fields in between are correct also. But write a main program yourself to test this. And then when you're convinced it works, you're going to go ahead and assess it. So the test bed is temp main202.0, which means when you want to build a testable image, you use this GCC command, gcc-o. You can call it anything you want. I'm calling it main202 just to keep it unique. And then the name of the test bed /temp/main202.0, and then the name of your functions file init.c. And then go ahead and run the assess command. Assess whatever the executable was and whatever your source file is called. So here's my init file. I'll compile with the test bed into an executable, so there's my main202. I'll do the assess command main202 init.c. It says ODP202 initialization of an array of structs. That's what I want to be doing, ODP202. So I'll use the G command. Lucky me, I got 10 out of 10. Okay, so there's a single test, 10 out of 10 or 0 out of 10. So exit out of that and you're done. So what does your init function do? Well, you have to define the structure, make init, parentheses, struct node, star, whatever you want to call your variable. And it's going to be a few assignment statements. To do this. And then a loop that does this on the last 99 elements. And then just return, you don't return a value. Doable? Yeah.
Yeah, that's doable.
Good? All right. Did you have a question beyond that?
No.
Okay.
I just didn't understand the complexity of the assignment until now.
Okay. All right, so that's ODP 202. So let's talk about PA1. So PA1, you're going to write code to work with linked lists the way we started talking about them yesterday, using an array of structures where each element of the array corresponds to a node. And you have three pieces to a node. You have a data piece, which says what's the number that's being stored in this node. You have a piece called next, which tells you where the next node in the list is. And you have a field called valid, which says, is this thing part of the list? It's how we keep track of what's in use in the array. So you're going to have a struct node which looks just like ODP 202 struct node, right? Data next and valid. Data is the integer, next is the next element's index, or -1 at the end of the list. So when we were working through this and we were making pictures yesterday, we had an array like this. We had something called data, something called next, and valid. And if this had a 4 and that was the first element, and the next field was equal to, say, 3, it meant the second node was down here at index 3. Maybe that was a 10. And we said if this was the last entry in the list, there's no number we can put in here for the next node because there is no next node, so I was putting in this value I just called null. Okay, we're actually going to use the value -1. Because if we use 0, well, there could be something at index 0. If we use 999, there could be something at index 999. So we use a negative number. And we just pick on -1 because we know we're not going to have an actual index of -1. So a -1 will mean that's the last node of the list. The valid field is a flag. 1 means valid, 0 means invalid. So again, in this structure, I was using check marks and X's yesterday. Since this is part of the list, I'm going to make valid 1. Since this is part of the list, I'll make valid 1. These other entries are not part of the list, so valid is 0. This is also a flag for whether this entry is in use or not. A 1 means it's in use, a 0 means it's free. And that's what we're really going to do with that. Okay, so I don't want you to write -1 anywhere in your code except in one define statement in the beginning where you define the symbol myNull to be -1. And when you want to set the next field equal to -1, don't say equals -1, say equals myNull. Okay? So define in the beginning of your file says anytime I say myNull, replace it with -1. So it's effectively the same thing as typing -1, but you don't want to embed a bunch of -1s in your code. Okay, so we're just going to embed the symbol myNull, and that's going to be something that will affect PA2. All right. And then you're going to declare an array of 100 struct nodes. Struct node, you can call it list or whatever you like, bracket 100 in your main program. Now list is your linked list. Right, list is this thing here. Right, it's an array of 100 of these struct nodes. So each entry of that array is itself a struct node, has a data, next, and a valid. All right, so I've written some of your code for you. I gave you the structure, the define, and the array declaration. What you need to write is the following set of functions: init, add, print, delete, and search. So before we go into the details of this, let me tell you the overall effect of your program. So you're basically writing two things. You're writing a set of functions that let you work with a linked list, let you add things to the list, initialize an empty list, print the list, delete from the list, search for things in the list. And then you're writing a main program that's going to use these to let a user create and manipulate a linked list by typing in commands. Okay, that's the program that I'm going to run when I'm assessing to see how your functions are working, whether they're doing the right thing. So you're doing two things for most of the programming assignments in this course. You're writing a set of functions to implement a linked list, and then you're writing a main program that uses these to allow a user to do things with a linked list. Okay, so a set of functions and then a main program. Let me show you what the main program should look like. So I say main, and it gives me a prompt. Okay, my standard prompt is a greater than sign and a blinking cursor. That means it's waiting for me to do something. So I'm going to ask you not to do things like clear the screen or print out a bunch of messages with some sleep statements in between or things like that. Let's try to stick to the specification in the assignment. So when you run the program, it should just print a prompt and wait. Okay, and if I type a question mark, it will show me what commands it understands. And there's only 5 commands I can use: I, P, S, D, and X. So this main program lets me put numbers into a linked list, and it's going to keep this list in sorted order. So if I have a list with a 2 and a 10 and I say insert a 5, it'll put the 5 in between the 2 and the 10. Okay, so I space number says add that number to the list. P says show me what's in the list. S searches for a number in the list. D deletes, and X exits the program. And anything else gives me this short synopsis of legal commands. So if I say print the list right now, there's nothing in the list. I haven't inserted anything. The list is empty. If I search for something, search for 34, it's not going to be in the list. The list is empty. If I try to delete something, it's not going to delete because there's nothing in the list. So let's put some things in the list. So give me a number.
15.
15. All right, so we put a 15 in the list. It said success. If I print the list, it's got a 15. If I search for 15, it's found. If I search for 14, it's not found. All right, give me another number.
69.
69. Give me another number.
70.
7. All right, so now if I print the list, it's got a 7, a 15, and a 69. And again, you can search for things. And if it's found, it'll tell you, and if it's not found, it'll tell you. All right, now if I try to insert another 15, it should say it's already in the list. And we don't want it to insert something more than once in the list. There's no reason you can't. It's just a requirement of the program. And if we delete that 7, we can say D7, it says success, and when we print, the 7 is gone. And if I delete the 7 again, it's going to say it's not found. And if I delete everything from the list, I'm back to an empty list.
Never mind.
Okay. All right, so I can insert a 5, I can delete a 5, I can insert a 5 again. All right, so it should do exactly what it sounds like it should do. Okay. So edge cases, right? Make sure that you can do things with nothing in the list. Make sure you can search, make sure you can try to delete, make sure you can print. Try inserting stuff, and make sure that it works when there's only one thing in the list, because that's an edge case. Search for something smaller and bigger than the thing in the list. Search for the thing that's in the list. And then do the same thing with 2 elements. And then do the same thing with 3. Now once it works for 3 elements, you're probably good. But try inserting something before the first number, try inserting something after the last number. You got to try all these cases. Make sure you can search for the first number, search for the last number, search for a number in the middle, right? Make sure it doesn't insert the number more than once. Make sure if you delete a node and then you search for it, it doesn't find it. And if you try to insert it again, it doesn't say it's already in the list. Right? So this is basically how I test your program. I sit there and I type billions of commands and I just put things into your list, delete them, try different things, right? And I get in this weird like zoned out state with this glazed look on my eyes, and I keep typing in all these things. And I'm not trying to break your code, but I'm basically trying to exercise all the different possible edge cases. So when you're testing this yourself, you want to try to get in that same mindset, right? What was the weirdest part of my code? It was really weird. I had a hard time if you deleted the first element, right? So play around with that, right? Once you think it's working, delete the first element. Try to delete the first element again, right? Try to search for that first element after you've deleted it. Try to reinsert it. Things like that. Is your hand going up?
Oh, no, never mind.
Okay. All right. So that's your main program, okay? So here's a really, really important detail. You're going to write these 5 functions: init, add, print, delete, search. Okay, you're doing something like init for your ODP, but your ODP does some extra stuff you don't have to. Init basically should just initialize a list. So take the element index 0, set the next field to myNull. Okay, that's all that your init has to do. But you're doing that and some other stuff in your ODP. Add should take an array of nodes and an integer and try to store that integer into the linked list that's represented by that array. And if it succeeds, it should return a 1. If it's out of space, if every element in the array is already in use, in other words, all those valid flags are set, it should return a 0, saying you're out of space. Print should just begin with the first node and print out all the nodes in order, side by side with a space in between, new line at the end. Delete takes the array of nodes and an integer looks for that number in the list. If it finds it, it deletes it and returns a 1. If it doesn't find it, it returns a 0, saying I couldn't delete this because it wasn't in the list. And search takes an array of nodes and an integer, searches for that in the array, and if it finds it, returns a 1, doesn't find it, returns a 0. So you're going to write these 5 routines, and then I want you to think about this as an interface, a way of interacting with a linked list that you're building. So what's your interface to a car? It's a key for the ignition or a push button if you're fancy. It's a steering wheel, it's a few pedals, maybe a clutch and a shift, a knob for the lights, a horn, right? That's your interface, right? And what is there between you and all the stuff that's doing this? Something called a firewall, right? It's a big heavy wall that protects the passenger compartment from the engine. If I wanted to sound the horn, I could climb out the window, lift the hood, take some wires from the horn, connect them to the battery, right? If I wanted to make the car go faster, I could go outside and find the lever that gets connected by the gas pedal, but maybe my car doesn't have that, right? Maybe my car has electronic fuel control, and I need to find some resistor and change the value of that, and now my car is going faster, right? We don't interface with a car by going under the hood usually, right, or crawling underneath, or pouring more gasoline, into this part of the engine. We use an interface, the pedals, the steering wheel, the buttons, and so on and so forth. That's how we want to think of these data structures as we're building them. We're building a linked list, and we only want the user to interact with it through these pieces of functions, right? These 5 functions, that's how the user will interact with the linked list. And it's really important, so you've got 2 roles here. You're developing the code for interacting with a linked list, but then you're a user who's using these things to write a main program to let the user say I5, P, D7, and so on and so forth, right? When you're in the role of the person writing the main program, this is your whole interface to the linked list. Your main program should never deal with this directly. When you try to insert, your main program should never say, for I equals 0 to 99, if valid equals 0, then do such and such, right? This does not exist to your main program. Your main program has no idea. This is on the other side of the firewall, okay? Your main program, if it wants to insert something into the list, it's got to use the add function. And before you add, you should make sure that this thing is not already in the list. How do you do that? Use the search function, right? You could do it by going into this array, and you're declaring this array in your main program. So you could just do a search through here and see if the data field of any of these matches your number. Don't do that, okay? Really, really important that your main program only uses these functions to interact with the linked list. So this is a central concept of object-oriented programming. Okay, when we get to 223, this is all that we'll be doing. But in 222, even though our main program could interact with our structure directly, we're not going to. Okay, we're going to require that everything we do with our linked list is done through these. Now these functions themselves absolutely have to know about this. Right, our add function absolutely has to go through and find a spot where valid is equal to 0, and then it's going to have to adjust the next field on some prior node and so on and so forth. But the main program, it just calls these functions. And so this is something called an abstract data type. When we think about a linked list as a collection of numbers in this case that we can initialize, we can add, we can delete, we can search, we can print, that's a view of a linked list in an abstract setting. Nothing to do with the fact that there's an array of struct nodes that have 3 fields and the valid flag is 0 and all that. That's detail, okay? Abstractly, a linked list is just this structure that we can do these things on. Initialize, add, print, delete, and search.
What do you want us to do if the user for instance, tried to add but didn't put a number?
Oh, so reasonable error checking. So if they say I, it's an error. Just remind them how to do it. If they say I, ha ha, that's an error. Remind them how to do it. If they say I 12, ha ha, go ahead and insert 12. Okay. But if they say I, ha ha ha, don't insert 0, right? Definitely pick that up as an error. If they just say I, don't just go ahead and use the last number that they typed in, right? And if you don't check for this, most of the times your code will, if you delete 12 and then you say I, sometimes it'll say, oh, I was equal to 12, so we'll go ahead and insert 12, right? So catch these errors, but don't worry about, if there's extra stuff on there. So the usual rule, if scanf likes it, you can accept it. And I actually mentioned that at the very end of the assignment. All right, so you got the idea of an interface, right? This is how you get to the linked list. Okay, so your main program prints a prompt, waits for the user to type enter, parses what they typed, and does the things that we already saw. So insert, print, search, delete, and exit the program. Insert, make sure it's not already in the list. How do you do that? Easiest way, if they say insert 5, call your search function. Search your array for 5. If it comes back with a 1 saying 5's in there, just print a message, note already in list. Otherwise, go ahead and do the stuff where you go through and you find the spot and you adjust the pointers and so on. Same thing with delete. If they want to delete 5, call your search function. If it says 5 isn't in the list, you're done. Just tell them node not found, and you're good to go. Okay, so catch these kinds of errors. Don't worry about this. Don't worry about this. I won't test those. Okay, makes sense so far? So deliverables, you need to turn in your implementation of all of those functions and your main program source code. Okay, got to have the source code. That's all I really care about, so that I can see what you've written. Lots of comments. Okay, so main program, comment block in the beginning. Make sure your name is in there, the date, the course, description in your own words of the assignment, all the usual stuff. Every time you write a function going forward, you should have a little block of comments in the beginning that describes the function. So if I have a function called search, right, have a block of comments in there in your own words just describing what this does. This takes an array of struct nodes and an integer, and it looks for that integer in the array. If it finds it, it returns a 1, otherwise it returns a 0. Because you're creating something that somebody else could use, right? You happen to be the one writing the main program, but you could take your 5 functions and hand that to somebody else who wants to use a linked list, and if they know what those 5 functions do, they can write their own main program, right? And they are going to be used somewhere down the road. You're doing something with a linked list, you've already got this code written, you'd like to go back and reuse it, right? And in Java, object-oriented programming, it's all about code reuse. And so you want to start getting in this habit of making sure that you document what you're doing. So functions, put a block in the beginning. What's the function do? What are the arguments? What does it return, if anything? What are the side effects? What are the special cases, right? You might make a delete function that can handle the fact that the thing you're deleting is not in the list. Or you might make a delete function that requires the thing you're deleting to be in the list. Right? It's easier to write it if you know that the thing is already in the list, because you're not going to run off the end of your list. You can just make a big forever loop until you get to the number. But maybe you don't want to have to require that the thing is in the list before you delete. Maybe you want your delete function to look for the case where it gets to the end of the list and didn't find anything. It's up to you, okay? But put it in your comments in the beginning. And then when somebody's using it, they say, oh, delete only works if the thing is in the list to begin with. They know they have to call search first to make sure the thing is in the list before they say delete. So lots of comments. And then on each line of code, unless it's absolutely clear what that line is doing, // put a few words, describe what that line is doing. And when your statement is something like, LL bracket next dot valid equals my null. What's a good comment to put there? Set element next valid equal to my null? That's not a useful comment really, because that's what the code says, right? You're not commenting what this instruction says, you're commenting why you're doing this. So a comment here might be mark end of list. Oh yeah, because I'm using my null as a valid for next, right, or whatever. That's gibberish code, but you get the idea, right? Explain why you're doing something, not just what that statement does. All right, bundle all that up into a tar file, include a make file. Okay, we're going to go over make files again tomorrow, just as a quick refresh. But I want your source files, any include files that I need, and a make file. Bundle it into a single tar, push it up to Canvas. If you haven't done this before, there's some how-tos from 224 posted on Canvas, or come and talk to me. Use WinSCP from Windows or SCP from Linux or Mac to move files between the Linux server and your own machine, so you can push them to and from Canvas, and then upload your tar by the due date. All right, so last detail. You're going to write these 5 functions, right? And these functions are going to manipulate this internal structure, this array of struct nodes. But I want you to write 2 other functions that you'll use inside these.
What's the 2 lines for after
LL. That's just what I called my linked list.
oh.
So, but you can call it whatever you want. So I want you to write 2 other functions. One is called getNode, the other is called releaseNode. So if this is our array of struct nodes and we're trying to add a new node to our list, what do we have to do? We have to find an entry where the valid flag is equal to 0. Right? If valid is 0, we know that index 1 is available. And so we can store our new data here and our pointer and so on. We could do that with a simple for loop. Start from the beginning, go through, look for the first entry where valid is 0, and then return the index of that. I want you to bundle that into a function called getNode. So getNode takes an array of struct nodes, looks for the first entry where valid is 0, sets that field to 1 to say this is in use, and returns the index of that entry. And in the case where your array is completely in use, there's no entries where the valid flag is equal to 0, this function should return my null, okay, which we know is -1. That's a flag saying there's no space left in the array that we can use. So if I call getNode, it should change this to a 1 and return a 1. If I call getNode again, it should change this to a 1 and return a 2. If I call getNode again, it should change this to a 1 and return a 4. And so on. And if all of these are set and I call getNode, it shouldn't do anything except return my null. So when you're looking for a new place to put something in your array, your code is going to call getNode, use the value that it gets back as the index. And then releaseNode is the opposite of that. You pass it an index number, and it basically sets the valid flag to 0. So if I delete this number down here, this 10, right, I'm going to make some changes to some pointers, but eventually I'm going to change this to 0. Instead of in my code saying set this equal to 0, I'm going to call releaseNode, and I'm going to pass it the index 3. The reason I want you to do this is because of PA2. Because in PA1, we're working with a particular implementation of this linked list. We're going to have a different implementation of the linked list in PA2, and I want the details of this finding a node and releasing a node in their own functions. Okay, if you stick to this, PA2 becomes much easier. All right, so tomorrow I want to talk about makefiles, just a quick review of that. And then we're going to start working with linked lists more. I need to tell you what a sentinel node is. okay, because it talks about sentinel nodes in the assignment. So we'll talk about linked lists and sentinel nodes, and then we'll start looking more at how we implement a linked list with this array, and we'll start writing some code to actually do things like search and insert and print and so on. All right, so we'll get into those details tomorrow. And there'll probably be another ODP tomorrow morning. All right, see you next.